Welcome, friends. We are now going to start a new topic for this course, Power System 1. So, we shall discuss in next few sessions. The topic name is distribution system. So, it is one of the main components of any power system. It starts with generation, then transmission of the power, and then finally distribution part. So that distribution system we shall discuss with you in few sessions, with few next sessions. So let us start with this topic, distribution systems. So what is distribution system? It is one of the main components of power system. So first we have generation, then so we have here generation. Next, then that generation of power, it needs to be transmitted over a long distance through transmission lines. So this is the transmission section. And after the transmission of power, we have distribution. So at this point or at this node or bus, this is the end of transmission. This is the end of transmission. And it is the beginning of distribution system. Beginning of distribution system. Now, again, this has two parts. This distribution network of power system has got two parts. First is primary and second one is secondary distribution. Now, primary distribution starts from this point and it is going to distribute power over a distance. Now, this substation is called distribution substation, and this transformer, that is the step down transformer here, 66 by 6.6 kV. This transformer basically it is a 3-wire system. It is a basically 3-wire system till this point. Okay. So the primary is of the transformer is 6.6 kV and the secondary is 415 volt. So the secondary of the transformer is 4-wire system. Okay, secondary of the transformer is 4-wire system. So in the secondary distribution part, we have a 4-wire system: phase R, phase Y, phase B, and the 4th wire is the neutral. Now suppose here we have a domestic consumer. We have a consumer 1. That consumer is getting single phase supply from R phase and from neutral phase, right? In this way, another consumer 2 is getting another single phase supply C2, and he may be getting supply from Y phase, and another is from neutral phase. And some other consumer 3 is getting another single phase supply, he may be getting supply from B phase, and another wire is from neutral. So in this way the entire distribution network is looks like. And finally, if we have a commercial load, like we have a big shopping mall, we have a big shopping mall, or we have a stadium, cricket or football stadium. There you will require all three phases, three-phase supply you will require. So in this way, this entire this distribution, secondary distribution network is formed. Now this diagram I have already represented at the very beginning of this course, which is called classical power system. This is the in a diagram where the typical diagram or different parts of the power system has been shown, starting from generation, then transmission, and then distribution. Now, since up to this, before discussing distribution network, we have studied or we have invested a lot of time on transmission network. Now we shall study distribution network very shortly. So to bridge that or to bridge that transient phase, we should compare the difference, or we should compare between transmission and distribution network in several parameters. Let us see what are the differences of between a transmission network and a distribution network. Now, if you consider the transmission network, the transmission network is mostly interconnected, and the distribution network is mostly radial or maybe weak meshed network. What do I mean by that? Now, mostly interconnected system means suppose we have a maybe later on I can produce the appropriate diagram for a interconnected power system, but for the time being, suppose we have a n number of bus. If we have a n number of bus, now out of that n number of bus, m number of transmission lines are there. So from one bus, maybe different transmission lines may be emanating, and that transmission line is terminating to another bus. So from that bus again, maybe 2 or 3 transmission lines may be emanating. So in this way, it is any 2 bus you will find it is mostly interconnected. That means you may get, suppose from bus 1 to bus 2, you need to carry some power in this way. So by chance, suppose this transmission line is out of service, so there may be some different routes. Through other buses, right? Through other buses. Let us say bus number 3. Then maybe from bus number 3 it is again going to bus number 4, then maybe again from bus number 4 to bus number 2. So even if the transmission line directly connecting between bus 1 and 2 are out of service due to any reason, so that still the transmission of power from bus 1 to bus 2 is possible through a different route. So this is called, it is interconnected system. The transmission network are mostly interconnected, highly interconnected. On the other hand, distribution network are mostly radial. What do we mean by radial? Suppose this is the supply. So if you have a conductor, you have a conductor like this, and different consumers are tapping from here. So this is called a radial system. So our distribution networks are looking like mostly like this, or maybe there may be some loop is there. There may be loop or mesh system is there, maybe 1 or 2. So that is why it is called weak meshed system. Maybe for entire distribution network you may see one such loop in this. Okay, so that is why it is called weakly meshed system, or it is mostly radial. On the other hand, it is if you find out the network, if you find out the transmission network, it is highly interconnected. Now let us coming to the next part, which is the transmission line and distribution line. Now the transmission lines, it should be transposed to in order to decoupled R, Y and B phase. On the other hand, distribution lines are untransposed in nature. Distribution lines are untransposed in nature. That is why R phase, Y phase and B phase are not decoupled to each other. That is why mutual exchange of energy between phases is not zero. So there is some finite exchange of energy between phases. It may be between R to Y or Y to B or R to B. It's like that. So in case of a transmission network, if it is a transpose, mostly transmission lines are transposed, there is no mutual exchange because of this transposition factor. However, the distribution network are untransposed. That is why the mutual exchange of energy between phases is not zero. So one can clearly say that then those phases are not decoupled from each other. So they are closely bound to each other. So that is the meaning of untransposed network. Now, as far as the load is concerned, the transmission line loads are mostly balanced. However, distribution loads are mostly unbalanced. Now, another one very important factor, that is X by R ratio. That X by R ratio for the transmission network should be very high. At least X by R should be greater than 10. On the other hand, it is extremely low. However, or if you can think reversely, that is the R by X ratio. R by X ratio for the distribution system is very high. R by X ratio is very high. It is just the reverse. For the transmission network, it is X by R ratio is high. On the other hand, distribution network, it is R by X ratio, that is very high. Now, if you compare with respect to number of buses, for a transmission network, the number of buses is low. However, for a big distribution network, number of buses are extremely high. That is another difference. Now, another important factor is fault. Now, fault is a natural phenomena that occurs anytime in power system. Now, to study fault, we have a technique, it's called sequence component analysis. Now, what is sequence component analysis? Sequence component analysis, essentially what it does, it splits R phase, Y phase or B phase, any phase into three different components, which is called positive sequence component, another you say negative sequence component, another is zero sequence component. So every phase is split into parts: positive sequence component, negative sequence component, and zero sequence component. For an example, if you have ZR, that is the impedance of ZR, R phase. So by utilizing the sequence component analysis, we can break that one as Z1, that is the positive sequence impedance, Z2 negative sequence impedance, and Z0 zero sequence impedance. So that sequence component analysis will work for transmission network, because these three networks are decoupled from each other due to this transposition factor. Due to transposition factor, impedance of individual phase can be split into three components: Z1, Z2, Z3. Since the mutual exchange is not available, that is why this positive sequence network, negative sequence network and zero sequence network are decoupled from each other. On the other hand, since distribution networks are untransposed, though the mutual exchange of energy is existing between any two phases, therefore this sequence component analysis will not work for distribution network, because these Z1, Z2, Z0 are not decoupled to each other, they are closely bound to each other. That is why if you analyze, if a fault comes in distribution network, and to solve that fault, if you apply sequence component analysis, that system or that technique will not work, or that method will not work. As far as the modeling part is concerned, to model a transmission line, it is very easy. Why? Because we always consider the single phase equivalent of a three phase model. A single phase equivalent of a three phase component. For an example, if we have a three phase transformer, then we can model this one as an equivalent single phase transformer. It is possible for transmission lines. However, for distribution network, it is not possible. So in distribution lines, we have single phase lines, we have single phase line, we have two phase lines, we have three phase lines. So you need to model each of these lines differently. You cannot take the equivalent circuit of three phase network into a single phase network. It is difficult. On the other hand, on the distribution side, there are many additional components or additional entities like distributed generation. We maybe have a solar energy, or we maybe have a wind energy. So due to these facts, so the modeling of the distribution network is not so easy as compared to the transmission network. So these are the few differences, or these are the few comparisons between transmission and distribution network. Now, before going to study the distribution network in a detailed way, we should look what are the different distribution types. So first of all, depending on the supply of the distribution side, we can classify whether it is a AC distribution system or DC distribution system. It depending on the type of the supply. Again, depending on the type of the network, we can classify our distribution system into radial or ring main. That means radial means a single conductor. From that conductor, several consumers are tapping. However, ring main, we have a mesh like structure. From that mesh, several consumers are tapping like this. We have a supply at some point of time. This is the VS supply point, and from the several other point, consumers are tapping. Now, depending on the magnitudes of the load, we may classify our distribution system like concentrated load and uniform load. What are they? Suppose we have a conductor like this. Now, if there are several tappings, let us say this is I1, I2 up to IN, where these I1, IN are different, then this is called concentrated loading. However, if we have a conductor like this, and if we tap the currents like this, so every current is equal. Wherever you tap, it is the same current. It is called uniform loading. So with this we conclude the first part of the distribution network. So what we have seen, what is the distribution network, and what are the components, or what are the differences between a transmission network and a distribution network, and the types of distribution network. And in the next few sessions, we will study different types of distribution networks with their example. Thank you.